We present a work titled Proprioceptive External Torque Learning for Floating Base Robot and its Application to Humanoid Locomotion. For the human-size humanoid robot, contact wrench feedback control is essential for agile and robust locomotion. Therefore, most humanoid robots are equipped with force torque sensors on each foot or joint torque sensors in each joint. However, such additional sensors increase not only the cost, but also the inertia, complexity, and failure possibility of the system. In this work, we propose an external torque learning method using a GRU network. The external torque is calculated by mapping the contact wrench from the FT sensor on the foot, and the measured external torque is used for the target value of the learning. The external torque is estimated only using proprioceptive sensors as the input features. Specifically, encoders in each joint, and IMU on the pelvis link are required for the external torque estimation, which are fundamental sensors of the humanoid robot. The random walking data is collected by manually commanding the desired velocity of the robot randomly on the flat ground. The step length, turning angle, step period, and swing foot height are varied around the normally used values to collect the large distributed walking data. 3 hours of random walking data is collected in 100 Hz, and the data is divided into training data and validation data with 9:1 ratio. This video shows the experiment comparing two contact wrench feedback methods, force torque sensor, and GRU neural network. The robot hardware is the same as the data collection setting. The step period is 0.9 seconds. As you can see, the walking motions between the two methods are undistinguishable. It is the same experiment with 0.7 second step period. Using the estimated external wrench of the network, the robot can walk stably as same as the baseline locomotion with the FT sensors. The estimated external torque and the measured external torque of the 0.9 second walking period during one walking cycle are displayed. As shown in this plot, the estimated external torque from the GRU network, the red line, tracks the measured external torque by the FTS, the blue line. On the other hand, the disturbance residual from the momentum observer, the gray line, has a larger error than the proposed method because of the model uncertainty. The estimated external torque can be transformed into the contact wrench, and as shown in the lower plot, the estimated external wrench shows a small errors to the measured value. To fully exploit the advantage of the proprioceptive external torque estimation, the real hardware sensor should be replaceable with the neural network. Therefore, 2 additional hardware settings are tested to validate the possibility of the removal of FTS. The robot is equipped with smaller and lighter feet links to mimic the FTS removal. Moreover, another hardware setting is also prepared where 2 battery cells are added to the upper body of the robot. This experimental setting is designed to show the adaptation ability of the trained network when the mass of the upper body is increased compared to the original robot setting. We calibrated the estimated external wrench for the small foot to reflect the modified kinematics and dynamics of the foot link. More details can be found in the paper. The small foot hardware setting is tested with 0.9 second step period. The GRU network can estimate the contact wrench precisely aided by the model-based calibration although foot links are changed. Therefore, the robot can walk stably similar to the FT sensor feedback. For the step period of 0.7 seconds, network estimation feedback performs consistently with the smaller feet. In this experiment setting, 2 batteries are added to the pelvis link. Even with the increased mass of the robot, the neural network can estimate the contact wrench correctly and makes the robot walk stably in both 0.9 seconds and 0.7 second step periods. This graph shows the ZMP and CP tracking errors for all experiments with hardware modifications. In many cases, the errors are similar to each contact wrench sensing methods. However, the errors are small enough for the robot to walk robustly. Thank you for watching the video.